Hello, in this lesson, we're going to do another one on mathematical inductions. We have talked about the mathematical induction principle and the steps, and we did 4 examples. And we actually did, I think we did 4 examples. But knowing the principle that we also need a variety of techniques, algebraic techniques, to carry out the proof. So in this section, I would like to go over the other questions on the homework, okay? The purpose is to expose you guys to the variety of other methods to prove using mathematical induction method. And what I recommend for you as you are watching these lessons, and you may like to pause before you watch the actual solution I do. So when I write down the answer, so this is going to be example number 5, continuing from the previous lesson. So this is to prove, right? Use mathematical induction to prove. Okay, and this one, I've chosen it to be the number 5 in your homework. Okay, this is how it looks like. It's 1/1 times 2. Okay, so please look at your homework. Okay, this proof would require a different technique, would require a different algebraic technique. But these techniques is not beyond our reach, okay? It's something we totally know how to do, but we may not be thinking of doing it. So I hope that these lessons will open your eyes to more techniques and more algebraic method you have used before, and try them. Okay, not every method fits all, and there are always new methods can be explored. So I hope this lesson will inspire you to discover more methods on your own, algebraically, or many other ways. Okay, so what I would recommend you is that when you see the question, you may like to pause the recording. Okay, pause the recording and try on your own. Okay, and try on your own for a while, for some time. Okay, if you cannot or don't know how to do, and you really don't know how to do, and you want to see the answer, and then come back to continue to watch, and you may come up with a different methods. Okay, so that's totally possible. You may have a different way to do this. And also, if you have to watch it and you see my methods, and then you say, okay, I'm going to try it if I can do it. So you want to pause the video, pause the recording after you watch the lesson, and try on your own again to see if you can reproduce. So this will be a method I recommend you to do for probably all of the recordings in the past and in the future. Okay, so let's get started. So you can pause anytime and I'm just telling you, and I recommend you do that. Okay, so now let's go about the proof. We understand that this is a mathematical induction method. So for the proof, we have 2 steps. Step 1 is we're going to prove is true for n equals to 1. Okay, so this is a statement. This statement says the left-hand side is equals to the right-hand side, right? We have n terms. So this is the first term, second term, third term. You can tell which term it is by seeing the n, right? The first term, this is 1 times 2. Second term, 2 times 3. Third term, 3 times 4. Nth term is n times n plus 1, right? So is it true for n equals to 1? Okay, is it, right? So we look at the left. Okay, the left, of course, only have one term left, right? N equals to 1, and that's equals to half. On the right-hand side, we're going to substitute when n equals to 1, right? N equals to 1. And it is also equals to 1/2. So left equals to right when n equals 1. So it is true for n equals to 1. Okay, and step 2, we assume, okay, the statement is true for k. The statement is true for k. Okay, that is, right? So you're gonna make that statement. So that assumed true statement, now replacing n by k. So this is assumed to be true. And then we're going to prove, right? It is true for k plus 1. So now n becomes k plus 1. Oops. K plus 1. Remove that part. Okay. N is replaced by k plus 1. So that piece becomes k plus 2. Now this is n going to be replaced by k plus 1. The bottom n will also be replaced by k plus 1. So the bottom becomes k plus 2. So this is to be proved, right? So left-hand side. Okay, so we got this left-hand side. Starting from the left-hand side, we'll see if we get to the right-hand side. Okay. And we want to see how we can apply it before this term, before the k plus 1 term is a k term, right? The k term should be 1 over k multiply k plus 1, right? And then we can regroup. Oops. We can regroup the first k terms and apply the assumed truth. Okay, apply the assumed truth. Okay, the assumed is going to be k plus 1 over k plus 2. Okay, plus, okay, so the assumed right-hand side has replaced the left-hand side, which they're assumed to be equal. And now we're going to add to the other piece. Okay, we're going to add to the other piece. And now we're going to find common denominator. Right, now we're going to find common denominator. Okay. So the common denominator will be k plus 1 times k plus 2. So on this piece, we have k plus 2. So we need a k plus 1 for the numerator and the denominator. Okay. So we just need k plus 1 in the denominator. So we have to make that 1 to have the original expression multiplied by 1. Anything times 1 stay the same. And then the second term stay the same. So now we have the same denominator. And we're going to keep that same denominator, which is a k plus 1 times k plus 2. Okay, and we're going to add the numerator. The numerator on this piece is a k plus 1 squared. Okay, k plus 1 squared. And plus 1. Okay, now we are going to FOIL the top. We're going to FOIL the top. When we FOIL the top, okay, we're going to get, we still keep the same denominator. So we're going to get k squared plus 2k plus 1 plus another 1. Okay. And now let's see what do we get. Let's see what do we get. Okay. I just feel something may not be working right. All right. So anyway, so let's see. We are getting here. Doesn't seem to be right. K plus 1 over K plus 2. Over K plus 1 over K plus 2. Okay, hold on. Oh, you know what? I did make a mistake. I made a mistake because I didn't feel right. I replaced the bracket by its equal, but I replaced by this one. It should have been this one. Okay, that's why. So it should be this one. Now, that one, my bad. Okay, so now with that said and done, I'm going to remove all of these and redo the whole thing. Did you see my mistake? Okay, I'm replacing the bracket by the assumed identity. Okay, so this should be K over K plus 1. I made a mistake by putting this to be proved one on the same place, and that's not right. Okay, so now we're going to make the same denominator. Okay, because we have K plus 1 times K plus 2. We had a K plus 1. So now we got the same denominator and we're going to factor, right? We're going to factor. We get the same denominator. So we have K times K plus 2 times 1, plus 1. Okay, so that piece is going to be gone. So we're going to have K times K plus 2. There you go. Okay, and then we will keep the same denominator and expand, you know, distribute the K to K plus 2. So we got K squared plus 2K and plus 1. Oops. Now we got the next one. Okay, factor the top. When we factor the top, it's a perfect square right now. So we got K plus 1 squared. So now reducing the K plus 1 on top and the K plus 1 on the bottom. So we will get K plus 1 over K plus 2. And we got the right-hand side in the to be proved part. So we proved it, okay? So of course you want to tell the reader that is, right? Just show them that this has been, oops. Okay, so this has been proved. This has been proved. And now 2 steps in the induction method has been proved properly. Then you can say therefore, okay? And the initial statement is true. The initial statement is true. But this method, this is just one of the methods, induction method. I want to show you another method, okay? The reason I want to show you the other method is because the other method is not induction method. Okay, so I'm going to show you the other method. The other method I'm going to show you is actually not induction method, but this method I'm about to show you actually is very, very useful, and you will encounter that in calculus 2. Okay, another method I want to show you, which is here. Okay, we know this is to be proved, right? So this time I'm not using induction method. Okay, I'm not using induction method. I'm going to use some algebraic maneuvering. I'm going to use some algebraic maneuvering, okay? So the left-hand side, okay, I'm going to work with the left-hand side. On the left-hand side, we got this piece, okay? So what do we notice is that, first of all, you see, this whole thing is 1/2. So it's really equals to what? This piece is equals to 1/1 minus 1/2. Okay, you can pause the recording to verify that. Well, it's just 1 minus 1/2. 1 minus 1/2 is 1/2. And this piece is equals to 1/2 minus 1/3. Okay, you may like to pause the recording to verify that, right? You find the common denominator. Okay, so let me show you. Let me show you on the side. So I'm just going to demonstrate that these two, right? This is 1/6, right? And this piece, if we are to, so I'm going to put it on note, okay? So this, you can do it on the scratch paper. If you put it on common denominator, right? So you have a 1/2. To make a common denominator, you times 3/3, and this is 1/3. You make a common denominator, you're going to multiply 2/2, right? 2/2. And now you have the same denominator. You have the same denominator, which is 2 times 3. 2 times 3, you see, I'm not, oh, denominator, sorry. Denominator 2 times 3. I'm not multiplying them, okay? We don't need to. And 2 times 3 in the numerator, in the denominator, numerator is 1 times 3, that's 3 minus 2. And that is the same as 1/2 times 3. Do you guys see that? And you can do this for all of these, okay? So we keep going. So 1/3 times 4 is equals to 1/3 minus 1/4. Okay, so the same thing would also apply. So we just keep going. Okay, we'll keep going. The term before this one, the term before this, before the last one, right, is going to be 1/n minus 1 times n, right? So that piece is going to turn into 1/n minus 1 minus 1/n. Okay, so I'm going to verify that for you, okay? So, and this last term is 1/n minus 1/n plus 1. Okay, so I'm going to verify this for you, okay? So this has been verified, right? This has been verified. So the second one is this piece, right? So now let's look at the next piece. The next piece I will verify for you. Make sure you have paper, pencil with you. And if you want to stop, right, pause and do your own, feel free to do that. So for these two, we want to make a common denominator. So the first one, the first term, we need an n/n. And the next one, we need n minus 1/n minus 1 because I'm trying to make a common denominator. So now the common denominator is found is n minus 1 multiply n. Okay, n minus 1 times n, right? N minus 1 times n. On the top is n minus 1 times n minus 1, so that's n minus 1. So you can see this would just equals to 1/n minus 1 times n. Okay, for this one, for the last one, is the same thing. It's the same thing. Okay, so common denominator is n times n plus 1, right? So we're going to multiply n plus 1 on the top and n plus 1 on the bottom. Anything times 1 stay the same. And then here, I'm going to multiply a n over n in order to make the common denominator. So here I am. I'm getting the same denominator already, right? So n times n plus 1, that's the common denominator. And the first term, we have 1 times n plus 1 minus n times 1, that's n. So in the end, we get this piece on the top, n minus n, that makes 0. So we have 1 left, right? So all of these are verified. I recommend you to verify this one by one by yourself and pause it if you have to. But now this comes to the beautiful part. Okay, this is the part you're gonna love. Okay, you're gonna love. Okay, we can open up all the parentheses, right? Because before every parentheses, they're just plus signs. So we can just open up all the parentheses. When we open up the parentheses, what do we see? We see negative half and positive half, that makes 0. Negative third and positive third makes 0. Negative fourth make the next one, next fourth makes 0. And all the way, so the term here will cancel with something in front of it, and this term will cancel. So in the end, right? So what you see here is that you just have 1 minus 1 over n plus 1. Okay, did you notice? Okay, so that makes 0, another 0, right? Another 0, and so this will be 0. So all the things in between will be reduced, gone. Okay, so now what do? We have only 2 terms left. Okay, and you can find common denominator. The common denominator for 1 is n plus 1 over n plus 1 minus 1 over n plus 1. So then now we have the same denominator. We are getting n plus 1 minus 1. So we get an n over n plus 1. Okay, this is very useful. I promise you, with 99% chance, you're going to see this similar thing in your calculus class, calculus 2. All right, so I've given you this algebraic method, even though it's not a mathematical induction method, but this method is very, very useful. Okay, but I hope you guys, can really get to know how to do it, and it's gonna add points to your future class. Okay, so this is one technique that you can use, one algebraic technique. And for the remaining of the questions, we're gonna start with example 6. Okay, example number 6. And this question is to use the induction method, right? So let me just take a shortcut, use math induction method to prove something. They're all the same, they're all same wording. Okay, so what do we want to prove here is it's not the same as it seems from what we've seen before. It's asking us to prove that n squared, not n to the power 3 plus n, is divisible by 2. Okay, so first we need to explain to you what is divisible. Okay, and of course we want this to be proved for all natural numbers, all natural number n, i.e. we want this to be proved for n equals to 1, 2, 3, 4, etc., etc. Okay, So first we're going to talk about what is divisible. What is divisible? Okay, divisibility, right? What does it mean that divisible by 2, right? What does it mean divisible by 2? Okay, example, divisible by 2. Suppose we have a number, right? Some number divisible by 2. What does that mean? Well, you can see that 4 divided by 2 is going to be another natural number. And then we say 4 is divisible by 2. Okay? So the result is a natural number. So the number you take, divide by 2, it come up with another natural number. So this means that 4 is divisible by 2. Right? Another example, right? We can say, hey, 6 divided by 2 is 3. And 3 as a quotient is a natural number. So we can also say 6 is divisible by 2 as well. Right? So for numbers that can be divisible by 2, what does that mean? You can see 6 divided by 2 equals to 3 can also be written as 6 divided by 2 equals to 3, right? What is more, you can see 6 actually equals to 3, okay, as a quotient, 2 as a divisor. Okay, we can write it 2 times 3 as well. It doesn't matter which order you put it. So 6 is divisible by 2, and the quotient is 3, and 6 is equals to the divisor 2 multiply the quotient. Okay? So now, in general, right, if a number, say P, is divisible by 2, what does that mean? Divisible by 2, what does that mean? It means that P divided by 2 is going to be equals to Q, and the Q is a natural number. In our case. Okay, in some cases they can be, it can be integers and it could be extended to integer. But here, because we're working with natural numbers, so we're just going to working within natural numbers. So if we multiply in this relationship, if we multiply both sides by 2, and we will end up to be P equals to 2 times Q. 2 times Q. Okay. This is to say that if a number is divisible by 2, then this number can be written as the product of 2 multiply another natural number. If P is a natural number. Okay, so let me write it down. Natural number P, okay, is divisible by 2, then, okay, then P is equals to 2 times Q, okay, where Q is a natural number. And we are going to need to use this property in this question. Then you say, what if we divide by 3? Similar, okay? In other words, similarly, okay, in similar nature, Similarly, if I say a natural number is divisible by 3, right? Instead of 2, it's 3 now. Then this will be 3 times q, and q is a natural number. Okay? Then you say, oh, natural number p is divisible by 4. Then this is going to be 4 times q. Right? So that's something we're going to use, and you're going to use some of those in your homework for it. All right, so now let's come back to example number 6. Let's come back to example number 6. Okay? Now, we're going to prove it. We're going to prove it. Now, first, we're going to try to show it is true. So step 1, the statement is true for n equals to 1. Is that right? When n equals to 1, n squared plus n is 1 squared plus 1, and that is equals to 2. And 2 is divisible by 2. 2 is divisible by 2, so that is true. Step 2, okay, so we're going to claim, we're going to assume, right? The statement is true for k. Okay, so the statement is true for k. Assume this is true for k. Right? And now we're going to prove that the statement is true for k plus 1. Right? So everywhere n becomes k plus 1 is divisible by 2 for k as well. All right? So that's the structure. You can see it's slightly different from what we did, but the nature, we're still using math induction method. We're still using math induction method. So we're going to prove this is divisible by 2. But first, let's look at what the assumption lead us to. Okay? What did the assumption lead us to? Because k squared plus k, if k squared plus k is divisible by 2, then we can use this fact, right? We can use this fact. How do we use that fact? Earlier on, we say that if a number divisible by 2, right? Natural number divisible by 2, right? I'm going to put it on, I'm going to set this on the side, right? As a little hint for us, right? So the natural number here is k squared plus k is divisible by 2. Then this p, right? So now in comparison, k squared plus k is divisible by 2. Right? It's divisible by 2. That's the assumption. Whoops. It's divisible by 2. What does that mean? Right? So I'm going to use then this k squared plus k is in the place of p, and that should equals to 2 times q. And where q is a natural number. Right? So now we have demonstrated. So we're going to use this assumption. So use this assumption and to put it here. So now we can say that this will be true because it is assumed a k squared plus k is divisible by 2 for all natural number k. Okay? So therefore we can have these. Okay? Now, of course, we're going to put our note little hint on the side, and we're going to work with this piece. Okay, so we're going to work with this piece algebraically. Okay, and we're going to get to k squared plus k. okay? How do we get there? We're going to FOIL. So we're gonna get k squared plus 2k plus 1 n plus k plus 1, okay? And now we have k squared plus 2k plus 1 plus k, right? So what we will do is that in this term, we have a 3k, but I'm not going to use the 3k. I'm going to bring the k, this k next to the k over here, because I'm going to take advantage of k squared plus k equals 2q. Okay, so that's the intention. And of course, 1 plus 1 is 2. So now I'm going to replace k squared plus k equals to 2q. Okay, so this piece will be replaced by 2q. So now it's 2q plus 2k plus 2. Now I can factor out the 2, and I will get a q plus k plus 1. That is that this piece okay is equals to 2 times a natural number. Okay, q is a natural number, k is a natural number, 1 is plus 1, that's going to be a natural number. And this only tells us that this quantity is divisible by 2. It's divisible by 2, right? So assuming that k squared plus k is divisible by 2, then lead us to k plus 1 squared plus k plus 1 is also divided by 2. So the principle of mathematical induction is demonstrated and is satisfied. Therefore, in the end, we could demonstrate, we could say that n squared plus n is divisible by 2 all the time for any natural number n. So this is how it's being proved. Okay, so if you look at the whole thing, right, it's about divisibility. It's about divisibility. Okay. The next question, I will work for you. Number 7. I think this will be interesting. This is also about divisibility, but this is about divisibility by 4. Okay, divisibility by 4. So I'm going to move over. So this question we're going to use divisibility by 4. So I'm going to bring that divisibility by 4 and tag along with us, right? And this is the example number 7. Okay, I'm not sure if the numbers are correct. Maybe it's right. Okay, so this one we want to use mathematical induction to prove something. Mathematical induction, use mathematical induction to prove what? 5 to the power of n minus 1 is divisible by 4. By 4. Okay, and then now by this time we're pretty familiar with the divisibility. So what I would recommend you to do is that you're going to pause the recording and try on your own. And then you come back. Okay, and then you come back. Now you're back, right? You have tried on your own, so you can watch me, if I made any mistake, right? Step 1, right? For n equals to 1. Okay, sorry. N equals to 1, right? Is it true? It looks like it's going to be true, right? True for n equals to 1. Why? Because when n equals to 1, 5 to the power of n minus 1 is 5 to the power of 1 minus 1. That's equals to 4. 4 is certainly divisible by what? Is divisible by 4. Right? So this is, of course, for all natural number n, right? So I'm just going to copy the whole question here, right? Step 1 is finished. Step 2, we assume that the statement is true for k. So 5 to the power of k is divisible by 4 for all natural number k. For natural number k, right? And we are to prove, right, that it is true for k plus 1. For k plus 1. Okay. We can just remove that. We can just remove that. Okay, just nice and clean. Okay. So what does it mean if we assume 5 to the power of k minus 1 is divisible by 4? Well, that just means that equals to 4 times q, where q is just a natural number. It's a natural number. We don't know what it is. Okay, but it's enough to know it's a natural number. So now we are to prove that 5 to the power of k plus 1 is k plus minus 1 is going to be divisible by 4. So we're going to do some algebraic manipulation. So you already know the whole drill, right? But here we're going to do one more thing, is that we're going to express 5 to the power of k. We're going to add 1 on both sides. Okay, on this relationship, we're going to add 1 on both sides. So we're going to have 1 plus 4 times q. Okay, 1 times 4, 1 plus 4 times q. And now we can work with 5 to the power of k plus 1 minus 1. So how do we express it? Well, we just normally just write it down. So this is 5 to the power of k multiply 5, then minus 1, right? So what did we use here? We really used that b raised to the power of m, b to the power of m plus n is equals to b raised to the power of m multiply b raised to the power of n, right? So that's what we used. And 5 to the power of k, what does it equal to? Well, we know that 5 to the power of k minus 1 is assumed to be divisible by 4. So we have this relationship. We're going to take 1 plus 4q to replace 5 to the power of k. And then we have a times 5, and we have a minus 1. All right. So then we're going to do some algebraic manipulation. I'm going to multiply 5 to inside the parentheses. So we have 5 plus 20q minus 1. 5 minus 1 is 4. So 4 minus 20q. And we can factor out the 4. And inside the parentheses, we're going to get a 4 times 5q. And this has demonstrated that 5 to the power of k plus 1 minus 1 can be written as 4 multiply a natural number. A natural number. So this is going to be, actually, this is an integer. Okay, my bad. This is actually an integer, but it's okay. It still demonstrates it's divisible. Okay. Oh no, I made a mistake. It should be a natural number. What am I doing? This is a plus 20. a plus 20, right? So this is a plus. So this is going to be a natural number. So no worries. I made a mistake. Sorry about that. So this means, right, you can say that is 5 to the power of k plus 1 minus 1 is divisible by 4. So that has been proved. Okay, now all two steps are done correctly. You can say therefore, okay, you can say therefore, and this piece is true. Therefore, that divisibility has been proved. Okay, that divisibility has been proved. Okay, you can see it does take some algebraic manipulation. It does take some algebraic manipulation, but it's not far off, right? It's not too far off. Okay. So we did number 7. Let's try number 8. Okay. Number 8 is saying that specific expression is odd all the time for all natural number. We know what odd numbers are, right? What is odd number? What is odd number? Example number 8. Okay, this is your homework number 8, and I also wish you guys to try on your own, okay, to prove it, and then come back to watch the recording. Or if you don't know how to do it, after you watch the recording, you'll try to prove your own as well. Okay, so example number 8, right? So all of these things we're gonna so practice that way. Okay, so this question we're gonna work with is that is n squared minus n plus 41 is odd. It's odd for all natural number n. What makes number odd number, right? What makes number odd? What makes a number odd? Okay, so I'm going to put a little note here before we show the work, okay? What makes an odd number? Well, odd number typically is even number plus 1, right? So if you have an even number plus 1, and that's going to be odd. If you can demonstrate you have an even number and that even number add 1, you can write it in that form, then you have proved it's odd number. But the question is, how do you demonstrate a number is even? Well, even number is divisible by 2, right? So how does a number look like if a number can be divisible by 2? We did that, didn't we? A number divisible by 2, we can write it down. How do we write it down? If a number is divisible by 2, which is an even number, and that number can be written as 2 times another natural number. So if this even number can be written as 2 times q, 2 times q is a natural number in plus 1. So odd number look like 2 multiply a natural number plus 1. Okay, so a odd number look like this. Odd number can always be written as a even number plus 1. Okay, so that's the hint. So let's see, if you want to prove it yourself, I may like to just pause the lecture and try on your own. Okay, make this a little challenge for you. Well, suppose you're back. Okay, you have paused and you have tried, and now you have a way to do it, and you've done it. Congratulations. So let's see how I would do it. Okay, so is it true for n equals to 1? Right? Is it true for n equals 1? We know that usually it is, right? But we still need to confirm it, right? So when n equals to 1, what do we have? This expression is going to turn out to be what? N is replaced by 1. This is 1. So 1 minus 1, that's going to be 41. 41 is odd, for sure. Okay, we don't need to demonstrate. If you like to write it down as 41, I mean, you can really just write 41 as 2 times 20 plus 1, right? So it is in the form of an odd number. But you don't really need to do this, okay? You don't need to do this. But anyway, so step 2. Okay, so we got step 1. Step 1. True for 1. Okay, so step 2, assume. Okay, assume the statement is true for k. Okay, this is true for k. For k, so now this is a k, a natural number. So what do? We are to prove, okay, that it is true for k plus 1. So we're going to replace n by k plus 1 everywhere. N is replaced by k plus 1. Okay, so that's what we are going to prove. So we are going to prove that this quantity is going to be 2 multiplied and a natural number plus 1. Okay, so now, what does an assumption tell us? If this is odd, if this is odd, so we're going to exploit, we're going to, exploit this piece as an odd number, right? Since this is odd, that means it equals to 2 times q plus 1, right? Where q is a natural number. We don't know what it is, but we don't care, right? We just know it's a natural number. It's there, right? And then we're going to leave some space to maneuver, right? K squared minus k plus 41 equals to 2 times q plus 1. I'm leaving some space just in case we need to do some maneuvering, right? For example, I can subtract 41 on both sides, but depends on what I'm getting, okay? So I'm going to work on this expression to see what I would need from here in any case. Now, we're going to FOIL, right? So the first parentheses, something squared that equals to k squared, k squared plus 2k plus 1 minus k minus 1 plus 41. Okay, we make sure we don't make too much mistake, okay? I make mistakes sometimes, and I'm sure you do too, right? We all do. So we got k squared, because we want to use this. We do. Okay, so we got k squared. Okay, so k squared, come here, please. Minus k, so I'm gonna put a minus k here. Plus 41, so we got a plus 41, right? And put everything else on the side, k squared. So we have a 2k. We want to leave that 2k, right? Plus 1 minus 1, that makes 0. So did we leave anything out? I think we're good, right? K squared, wait. 2k squared, this is a minus k, sorry, minus k minus 1, right? Minus k minus 1. So we want to make sure we keep these equal sign, right? So k squared goes here, minus k goes here, plus 41, right? So we have 2k plus 1 minus 1, plus 1 minus 1 makes 0. So now we're good. Now, this piece, we can use the assumed fact. Okay, assumed fact. So we're going to put this in parentheses and substitute everything in parentheses, substitute the parentheses by its equal. So we're going to take 2q plus 1 and then plus 2k. Now what do we get? We have 2q, 2k. So we're going to take out the 2 from, and then q plus k, and then plus 1. Q is natural number, k is natural number. So q plus k is a natural number. So 2 times a natural number for sure is even. An even number plus 1 is odd. So now we are certain, right, with the assumption that this piece, right, you can say that is, that expression is odd. Okay, and we don't need anything manipulated here. So we're good. So now we can draw the conclusion. Therefore, right, what is to be proved? We'll just copy, right? We just copy that. This piece is odd. You can see that in this series of proof, you've been introduced to a lot of mathematical or as algebraic techniques, right? And also some new concept. If it's not new to you, and this is review, right? But this might be divisibility. I think you have learned it before, you might have forgotten. So this is a perfect opportunity to review it. All right, so number 9 is about divisibility. It's about divisibility. So I'm going to do it for you so that you have that example in your, for your reference. But still, I actually would like you to try it yourself before you watch my answer. Okay, so this time we want to prove that n raised to the power 3 minus n plus 3 is divisible by 3 for all natural number n. Okay, so now we understand divisibility very well, right? We understand divisibility very well. So I'm still going to bring the divisibility by 3 to our, in case we need it, natural number divisible by 3, right? We're going to bring that definition with us. Bring that definition with us. All right. So how about you pause this lecture right now and try it on your own? Okay, try it on your own. So pause it, right? Try it. Okay, so now pretend you're back. Okay, so now is it true for 1, right? Step 1, true for n equals to 1. Okay, so is it? So when n equals to 1, what do we get? When n equals to 1, this expression, we're going to replace n by 1. 1 equals to 3. And 3 certainly is divisible by 3, right? So it's true by 3. Done. Step 2, assume. Okay. The statement is true. Is true for k, i.e. that this piece is divisible by 3 for k. So this is a k, this is a k. To prove that statement is true for k plus 1. So n is replaced by k plus 1. N is replaced by k plus 1. And that's also divisible by 3. And of course, as you know, you can predict that because it's divisible by 3, so this piece, we're going to write it down using the definition of divisibility by 3. So as 3 times q. 3 times q, where q is a natural number. It's a natural number. Okay? So now we're going to work with this piece. Working with this piece, okay? And we're going to have to foil. Right? And what do we get for foiling this? Okay, you may like to pause the recording just to expand this, and I'm going to just take a shortcut, okay? I'm going to take this shortcut. So the next step is going to be this piece, right? So this cubed is equals to that. So I have a minus k minus 1 plus 3. Knowing that we're going to use this fact, right? From the assumption, and we're going to make that case to happen. And we will have k to the power 3. I'm going to move k to the power 3. Now let me do it this way. Okay, so I'm going to move about so you can see how I move things about. Okay, minus k is needed, right? So I'm going to minus k, I'm going to put it here, right? And we need a plus 3. So I'm going to have a plus 3. So I'm going to have a plus 3 over here. So that piece I can use the assumption. And the rest of it, oh, plus 1 minus 1, that makes 0, yay. So we're so close, right? Now, k to the power 3 minus k plus 3, and that's going to be 3q. And then we got 3 times k squared plus 3k. Now you can see we have a common factor, 3. 3 will be factored out. So we have a q plus 3k squared, plus k squared, sorry, k squared and plus k. And that certainly tells us that this expression is divisible by 3, right? So you can say that expression is equal to 3 times a natural number. Okay, we don't know what that is, but it's going to be a natural number, right? So therefore, you can say, you know, the principle has been fulfilled. Now we can say n to the power 3 minus n plus 3 is divisible by 3 for all natural numbers by mathematical induction. And last one, number 10. Okay, number 10. So here I'm going to put it on the note. We don't really need this, right? So the whole of the proof is right here, right? The whole of the proof is right here. So now, are you ready for number 10? This is the last one. The reason I keep this one because I figure you might need that for Calc 2. So you have a little preparation over there. Even though you might forget by the time you're taking Calc 2, but I think I still think it's nice to know it right now. And so next time when you use it, it's not going to be too strange. It's not going to be too strange. Okay, so this is example number 4. This is going to be our number 10. This is going to be our last one. Okay. You will need a lot more in the future. Okay, when you're doing Calc 2, series and sequence and all that stuff. But this one, I thought would be nice to know. Okay, it can be very useful. it can be very useful. Okay, for all natural numbers n. There you go. So proof. If you like, you can pause the lecture recording right now. As always, as I recommend, always that just try it yourself. Okay, so now pretend you're back. Step one, are you back? Have you paused it, right? Feel free to do that because a lot of these things you need to study over and over and over again. Okay, so now, is it true? Is it true for n equals to 1? Most likely, yes, right? Actually, it's true. True for n equals to 1. N equals to 1. Okay, why? Let's demonstrate. Right? When n equals to 1, what will happen? The left-hand side, right, is 1. The right-hand side is 2 to the power 1. And that is certainly true, right? That is true. Step 2. Step 2, right? We assume the statement is true for k. What does that mean? If it's true for k, means this piece is true. This is a k and this is a k. 2 to the power of k. Okay? To prove the statement is true for k plus 1. So to be proved is right here, right? So this is going to be k plus 1, and that's going to be k plus 1. You see, in this case, you're dealing with the inequality. You must resolve to be good at inequality. In this semester, we've done a lot of inequalities, okay? You must resolve to do inequality well. You're going to need that for calculus classes, okay? All right, so we are to prove this, right? We are to prove this, to be proved. So now we're going to use this, right? We're going to use this. So we're going to work with inequality. So from this piece, what can we do? Right? To prove inequality, we may like to start from here. Right? We may like to start from here. And on this piece, since this is assumed true, right? Since this is assumed true, how about, because from k, 2 to the power of k to 2 to the power of k plus 1, we need, what do we need? We need to multiply a 2, right? So if I multiply a 2 on both sides, right? And the right-hand side is going to be 2 to the power of what? K plus 1, right? So we may think about how to do it, but the question is 2 times k. This only shows 2 times k is less than 2 to the power of k plus 1. What do we want to prove is a k plus 1, right? So how is a k plus 1 related to 2 times k? You know what I mean? So if we can show that 2 times k is larger than k plus 1, you know what I mean? Right? Can we show that k plus 1 is less than 2 times k, or less than or equal to 2 times k? then we'll be good. Right? Can we show that? Can we show that? Well, 2 times k is equals to k plus k. Right? K plus k is 2k. For k plus 1, 1 is the smallest of the natural number. So this is in fact true. Okay, so let's make the narrative. Let's make the narrative, right? So you can see we're almost there. Okay, so now I would say since k is at least 1, right? Natural number 1, 2, 3, 4. Therefore, k plus 1 is less than or equals to k plus k, right? Since k is greater than or equals to 1, so k plus 1. So I'm just to make this, since k is larger than, so I'm going to replace 1 by k. And that means this is a 2k, i.e. k plus 1 is less than or equal to 2k. Okay, according to the assumption, right? Because we got here from the assumed, and therefore it's less than 2 times k plus 1. Okay, that is, right? That is k plus 1 indeed is less than 2 to the power of k plus 1. Proved. Okay. So we use the assumed. Right? So let me just fill with one more line. From the assumed, right? We multiply both sides by 2. Right? So 2k, but the assumed is assumed to be true. So we multiply 2 on both sides. So 2k less than 2 to the power of k plus 1. And then we prove that k plus 1 is actually less than or equal to 2 times k. And therefore, we can use this relationship to have proved k plus 1. So now we have proved it. This identity actually is pretty useful in Calc 2. Okay, therefore, we can say that this is proved. So you can, so in this mathematical induction method, and from these examples, you can see a variety of situations. Okay, the first lesson we covered certain types, and in the second lesson, which is this time, we covered that, divisibility, we covered inequality, and algebraic, manipulation that sometimes is necessary in this work. So I hope that you guys will really practice and get the skill and get ready for your calculus class. Okay. So once again, I hope you guys will do your own practice, pause the recording, from time to time to check on yourself, because you really need to check on if you can do it, right? If you can do yourself independently. Okay, so that was my recommendation. Thank you for watching. And the last question as a whole, you can see it's right here. It's right here. Okay, so until next time, thank you for watching.